In this video, we're going to talk about what happens when you change the number of subatomic particles. So in the last video, we talked about how you identify the number of protons, neutrons, and electrons. Here we want to talk about what happens when you change each of those values. So we'll start with electrons. An atom that has gained or lost electrons is called an ion. When you change the number of electrons, you're changing the charge, but not the mass of the atom. If you gain an electron, since electrons are negative, you're going to become negative. If you lose an electron, since you're losing a negative charge, you're going to become positive. So ions are basically atoms that have a charge, or atoms that have gained or lost an electron. When they gain an electron, become negative. If they lose electrons, become positive. On the other hand, isotopes have to do with changing the number of neutrons. So atoms that are the same element but just have a different number of neutrons are called isotopes. In the last video, we talked about the fact that when you add the protons and neutrons, you get the mass. So since you're changing the number of neutrons, you're going to change the mass of the atom. Changing the mass of the atom doesn't affect the charge, though. So changing the number of neutrons has no effect on charge. And lastly, when you change the number of protons, you're going to change the element. This changes you into a new element because protons are what we use to identify what the element is. So let's say we're talking about carbon. We could say, well, carbon has 6 protons. If we start talking about something that has 7 protons, well, now we're looking at nitrogen. So we've changed the identity of the element we're talking about. So if you change the protons, you become a new element. If you change the number of electrons, we call that an ion. And when you change the number of neutrons, we call that an isotope. When we're naming isotopes, there are standard ways that we represent the way that an isotope is written. So when you see an element's name, for example, carbon, and then a dash, and then the number, so carbon-12, the number just indicates what the mass of that atom is. So you could say carbon-12 means carbon with a mass of 12. Carbon-14 indicates carbon with a mass of 14. So we could write the element dash, the number, and that indicates the mass. Sometimes students are forgetting that this number indicates mass. So it's something for you to make note of. The number after the dash represents the mass. On the periodic table, we have elements listed. And we're going to measure the mass of the elements in a unit called the atomic mass unit. We used to abbreviate AMU. On table D, we're now going to abbreviate it with the unit, just the letter U. So when you see U or 1U, that represents 1 unit or 1 atomic mass unit. The atomic mass unit, or how much an atom weighs, is based off of, or we have like a reference for which we use, and that's carbon-12. On your actual periodic table, if you open it up, and you look at the periodic table, there's a key, and it will tell you on the key that we're using carbon-12 as a reference or based off of carbon-12. We'll point that out to you tomorrow in class so that you can see what we're talking about. But we should know that our reference for talking about atomic mass is carbon-12. So basically, if we want to know what 1 atomic mass unit is, we're going to say it's 1/12 of the atom carbon-12. So carbon weighs 12. What's 1 AMU? 1/12 of that. And lastly, we want to talk about how we develop the numbers that are listed on the periodic table for mass. So if you look on your reference table, you'll see that carbon, for example, is 12.01. It's not just 12, and we've already talked about the fact that, well, mass equals protons plus neutrons. But what we need to talk about is there are different amounts of each isotope on Earth, meaning that there are different percentages, abundance, like how much there is of various isotopes. So let's say you're calculating your grade in class. Your grade is based off of the same principle that we use to show what the actual atomic mass is on the reference table. When we're calculating grades, we'll say, okay, let's say tests are 70%. You'll take your average of test grades and you'll multiply them by 0.7 or 70%. And let's say homework was 30%. You take your homework grade and multiply it by 0.3, and then you add it up. We're going to do something similar for isotopes. Let's say we have isotopes of potassium. One has a mass of 39, one has a mass of 41. We're going to calculate what the average atomic mass should be on the periodic table. That's the number that we're going to actually put in the reference table on the atomic mass spot. If I straight up took an average, 39 plus 41 divided by 2, I'd get 40. But we don't. So what they do, or the method that we use, is taking the isotope's mass, which is not actually 39, but 38.64, and multiply it by how much potassium there is on Earth. So 93.12% of the Earth, or of the potassium on Earth has a mass of 39. Then we take the potassium isotope with a mass of 40, so it's 40.9, well 41 is 40.962, and we multiply it by the percent abundance, which is 6.88. And then what you're going to do is you're going to add that up together. So let's show you the math. We multiply it, and then we add it. When you multiply by a percent, we know in math to get something to be a percent, you're multiplying by 100, so it's the answer here is 93%, then we have to get rid of that percent in our calculation. So I'm going to make it 0.93. So this is where the 0.93 comes from. You're moving the decimal 2 places to the left or dividing by 100 to get rid of that percent, multiplying it by the mass, and you do the same thing for the other percentage, 0.06. So move the decimal 2 places to the left, times it by the mass, and then you just add them up. And that's how you calculate the average atomic mass. So we want to note that the number on the periodic table is actually a decimal spot because it's an average of all the naturally occurring isotopes that exist for that element. Potassium only has 2 isotopes. If there was another isotope, I would do the same thing for the next one. Take the percentage, move the decimal 2 places to the left, multiply it by the mass. Now you'll notice that mathematically, the answer that you get for your average atomic mass is going to be closer to the isotope that there's a greater percentage of. So since 93% of the potassium on Earth has a mass of is at 93% abundant, like the more abundant it is, the closer the math will give you to that isotope. So if my answer is 39, that's because the majority of it has a mass of such. If you look at your reference table, basically you could figure out what isotope is most abundant. So if I look at carbon, since the math came out to be 12.01 on my reference table, I would say carbon 12 is most abundant. If you looked at nitrogen on your periodic table, since the nitrogen, the mass is about 14, so we'd say nitrogen 14 would be most abundant. Lithium 6.9, I would say, if I had to round it, lithium 7 is the most abundant isotope. So in summary, by looking at the number on your reference table for atomic mass, if you had to round that to the nearest whole number, that would give you an indication of what isotope is most abundant.